Welcome everyone for the QML session series we are starting today. And today we have with us Catalina Albornoz from Xanadu. Catalina holds a master's degree in electronics from Los Andes Universities and an engineering diploma from IMT Atlantic in France with a research focus on autonomous systems. She is currently the quantum community manager at Xanadu, where she is helping build the community around Penny Lane. And in the past, she also worked as an IBM quantum ambassador. And Catalina has been the reason championing the entire relationship and the partnership between Xanadu and Womanium for the past 3 years. So we are very happy and really honored to have you back, Catalina, for this QML session. So yeah, over to you, Catalina.
Thank you very much. And to everybody attending. Today, the goal is that you get all of the tools, the learning, the building blocks that will help you do projects, do research, learn about this very interesting topic, which is quantum machine learning. And we're going to challenge some of the assumptions, some of the knowledge that we think we have. So before we begin, I'm going to ask everybody, well, first, let me introduce, I know that Vardaan introduced myself, but I just want to focus on a couple of things. I didn't study quantum machine learning, right? But I'm an engineer, but I could still make it into the field. I'm not doing research. I'm working in community, helping, everybody who's joining the field, and managing a lot of the activities that we host from Penny Lane and Xanadu. And this is an invitation for you as well. If you come from a different field and maybe you have this assumption that quantum machine learning is going to be too hard, it's not. It's probably going to be easier than you think, and maybe harder in unexpected ways, right? So this is an invitation to just enjoy, learn, and challenge yourself. You're very much welcome into the field, and we need people with different and new ideas coming from different backgrounds. So today, I'm going to first give an intro of what is Xanadu, what is Penny Lane. I'm going to talk about some QML basics, so knowledge or terminology that you may not have heard before, that is going to be, the building block for what you're going to need to know later. We're going to do a live demo, so I'm going to show you some code, show you how it looks, how it works, and how it doesn't work. And at the end, I'm gonna share some resources and what I call the homework. It's I'm not gonna check the homework, but it's gonna be more like a suggested homework. So let's get started. Xanadu is a startup. It's a Canadian startup founded in 2016. We have almost over 200 people now already who have a very strong mission. We want to build quantum computers that are useful and available to people everywhere. So you're part of the mission, making our software and hardware available to you, and our knowledge and expertise and education available to you. That is part of our mission. So we're very happy to be here. Our hardware is focused on photonics, which means we use light to make quantum computers. And we have a full stack. We have the hardware, the software, and the applications and algorithms research. So the hardware is going to work differently from what you may have, being used to. And we're not going to focus on how the hardware works today. If you are interested in this, then go to xanadu.ai. That's a company website, and we have a lot of videos and explanations. But the main thing to know is that we're in the process of building a new generation of quantum computers. We're in the process of building our first fault-tolerant modules. And our architecture is universal, meaning what you program in Penny Lane or what you have programmed in other software, you should be able to run it in those new computers. They're not online, they're not ready, we are building them, right? Building a quantum computer is hard, it takes a lot of time. In the meantime, and not in the meantime, but also a very important thing that we need to do is develop software that is going to allow us to develop meaningful applications, right? So why do we even do quantum computing, right? ask yourself the question if you want to post an answer in the chat. Why do we even do quantum computing? The goal is to solve some very hard problems. Not all problems, only specific problems that classical computer cannot solve. And not even all problems that classical computer cannot solve, just a subset of those. One of those, there's one. We hope that quantum machine learning will be one of those, and we think it's going to be a key target area. But there's still a lot of work to do. Some other areas are quantum chemistry. That one is more obvious, of why in chemical systems you can use quantum computing. And in the end, we integrate all of these layers together. So the hardware, the software, and the algorithms. Especially today, we're going to focus on the latter two. The software and the algorithms, they need to work together. And so what we do, for example, we have some of the best researchers in the world in quantum machine learning and quantum chemistry. Maria Schultz, for example. Maybe you can give me a hands up or a reaction if you have heard of Maria Schultz. I don't know if I can see it, but maybe you can let me know. I can see the hands. Perfect. Yes. So yeah, give me a reaction if you have heard of her. Good. So she works at Xanadu, and there's a whole team working on quantum machine learning. We work not on a specific, let's say, not on a specific problem, a specific application, but like the foundation of that. And all of the research quickly turns into something that goes into the software. So you're going to see that we have tutorials, demos, and even like the software itself evolves as the research evolves. We want it to always be at the frontier so that you can do impactful, projects and research with it. So why do I say research so much? It's because today this is still a field of research. This is not a solved problem. Everything that happens in quantum machine learning is in the area of research. There's not one product that will work for everything. Everything we're doing still, we're learning on the way. And now zooming in a little bit here. What is Penny Lane? I mentioned Penny Lane. Let me ask the question again. Who knows Penny Lane? Maybe lift your hand if you've heard of Penny Lane. Give me a reaction or a hand up. Yes. Perfect. I love it. All right, great. So did you know that Penny Lane had all of these things? Penny Lane is the software. Penny Lane is the SDK that we use to program. Penny Lane has high performance simulators. So useful if you have, for example, an HPC computer, many other things. We have a compiler. So Catalyst is this kind of brother software that goes with Penny Lane. It integrates with it. It works very well together. And we have plugins. Plugins help you code in Penny Lane and run your code in other places. And PennyLane.ai is a website or hub for learning, for content, for engaging with other people, etc. So all of this is part of the Penny Lane ecosystem. And people love it. I guess you too, there's probably a lot of you who have been part of or are part of the Penny Lane community, asking questions, answering questions, doing projects, maybe studying in a university where Penny Lane is taught or used for teaching. It's a tool and it's a community as well. So now getting into the topic, let me now I'm going to ask you this question, so you can go to that Menti. Sorry, because the bar on top is not letting me see. All right, so I'm going to launch. I am going to, no, not that one. I don't know if you're seeing anything. Here. What words come to your mind when you think of quantum machine learning? So here you can scan that QR code or go to menti.com and put in that number. I want to hear what words come to your mind when you think of quantum machine learning. So
And
as we
many
get more answers, I will see them here.
Many people are typing in the Discord chat as well. We will share some of them. Varda says variational algorithms. Maya says optimization. More are coming, but currently people are trying to log into Menti. I see VQEs. I see many people typing.
Here, I think this link should also work. I'll share it in the chat. Yes, we get some answers. AI, quantum neural networks, optimization. Futuristic. Nice. Hype. Oh, some of it, yes. We're going to try to break it up today a little bit. Oof, perfection. I had never seen that one. Crazy. Ansatz, yes. Faster, speed up. Those come up often. Variational algorithms, yes. Oh, great answers. Amazing. Okay, so a lot of optimization, and that is true. Optimization is actually the big base, the building block that you're going to use for quantum machine learning. And variational algorithms, data, those are all very important as well. So what is it exactly? So let's go to the next stage and try to say what is quantum machine learning? It works in the interface between classical data and algorithms and quantum data and algorithms. So, for example, if you use classical machine learning to improve a quantum computer, technically that's quantum machine learning. Most of us probably don't think of quantum machine learning in this way, but that goes within the definition of it, right? What if you use quantum data and use classical algorithms to treat it? That works as quantum machine learning as well. What we think, often when we think of quantum machine learning, we're referring to using classical or quantum data and running it with quantum algorithms. So that's what most people refer to when they say quantum machine learning. But all of these are quantum machine learning. So today we're going to focus on the most popular one, but you can actually use, and we have people at Xanadu, for example, who use machine learning to help improve stuff in our quantum computer. So if you're into machine learning, there are many ways in which you can combine the knowledge of quantum and classical. Here we have some very important concepts. So first, actually, give me a hands up if you are comfortable with quantum circuits. Give me a hand up if you're comfortable with quantum circuits. Okay, perfect, a lot. And now give me a hands down or a reaction down or a sad face if you are not comfortable with quantum circuits. Or Vardaan, maybe you can tell me if you're not comfortable with quantum circuits. That's totally okay, just let me know. I guess everybody has already had a couple of sessions.
Yes, working hard the past weeks to be introduced to them.
Nice. Perfect. Awesome. So here in the left-hand side, what we're representing is we have a quantum circuit. These, yellow, pink, and blue blocks represent. So first, we're going to have an embedding. So we're going to put data into the quantum computer. It's going to create a specific state in, our quantum circuit. Then we're going to have some layers. So these pink and blue, they can represent a different set of gates, a combination of gates, and they can take parameters. So these alpha and beta, what they're going to be is they're going to be some values that we're going to put into the quantum computer and we're going to modify. So we're going to do some tuning, not manually, but automatically. So instead of having a manual tuning for the alpha and beta, quantum machine learning and optimization allows us to do that tuning. where is the difference? And this is a common question. Where does optimization stop and it becomes quantum machine learning? Data. Data is the key in quantum machine learning. It's you need data, probably a lot of data usually, depends, in order to, for it to be considered quantum machine learning instead of just an optimization problem. So the picture that we have in the middle represents an optimization landscape. This is a cost function. So again, an important concept that we're going to hear a lot in quantum machine learning. Our cost function is going to tell us how well we are doing. So let's say in the circuit that we have on the left, we want to measure, we want the measurement to be 0, right? We want to be as small as possible. So we want to tune these parameters, alpha and beta, so that the output is 0. Oh, sorry. Now, our cost function is going to, tell us or give us a map of what is the output depending on the value of alpha and beta. Except we don't know this, right? Usually for a specific circuit, a specific problem, we don't know exactly how this is. So an optimization routine will allow us to start at any point and then move along downhill. So downhill, we're going to find something called a gradient. This gradient is the direction of maximum change, and we're going to go downhill against the gradient, right? So if we're rolling down a mountain, we want to roll as fast as possible. We're going to go step by step. And so what happens is, let's say I start at a point in the pink region, right? This means there's a specific value of alpha and beta. So I'm going to have some initial parameters. Very, very important concept when you're talking about variational algorithms. You're going to start with some initial parameters. Then you're going to take a step. So let's say it's one little square in a direction, which I think this one is the one that is, has the steepest descent. So I'm going to take one step in this direction, and I'm going to stand here now. So after that one step, I will have a This means I have to run my circuit again. The layout of the circuit will be the same, but the specific value of those parameters is going to be different. And step by step, I'm going to get to a lower cost until I get to a place where I'm at the bottom and there's no way to move down anymore. Yeah, so basically that would mean a success. Now there's making these cost functions is a whole science. And there are cases when that cost function does not look so nice. It actually looks pretty flat. And if it's pretty flat, it's hard to know where downhill is. Or for example, you have kind of what we call local minima, meaning you have places in the function that, kind of are at the bottom of their little region, but they're not the overall bottom. Usually there are techniques to overcome this, but choosing your cost function is very important, and it will depend on what is your purpose, right? So in this case, our purpose was to get the circuit to have a value of 0, for example, or a specific value. Sometimes what we're going to do, often what we're going to do, is we want the circuit to have a specific value depending on the input. For example, if my input is numbers from 1 to 10, and I want the output to be the sign of the input, then I will have to train in a specific way for that. And so it depends on what you want to do. Then you have to build a different cost function that will take you there. Now, what you see on the right is a different representation of this. This psi that you have at the beginning means you have an initial state. You have to prepare it. So this is something very important. You usually don't have these states for free. This is going to be a very hard thing to do. Embedding data into the quantum computer is going to be a roadblock, a very big bottleneck. So very important to not to assume that we can always prepare initial state easily. Then we have our gates, and this part you probably already know from your previous sessions. And at the end, you have, a new version of the state at, right before measurement. So you can use techniques, for example, gradient descent. There are other both gradient-based and non-gradient-based techniques to find the new version of those parameters that you're gonna then use for the next iteration of your circuit. All right, so this is very important because differentiable programming, so far it has been revolutionary. It is how we are thinking of quantum machine learning, and it has its pros and cons, but it's important to understand it so that you can either use it or challenge it. All right, so I guess we don't need to go over qubits, circuits, and gates. We can go straight to embeddings. Let me stop here for a second and give me a hands up if we're doing well, or give me a reaction to show me how you're doing.
Hey, everyone on Discord, how are you doing? Going well? Ready to go into embeddings right away? People say, I love the penny lane visualizations. And people ask, are they done by hand or by software? And Kush asks, is there a way to find global minima for the cost function?
Yes, good questions. So we have a designer, and he does all of the drawings by hand. I mean, in an iPad or equivalent. But yes, we have originally it was actually the person who is now our head of product. He started doing the designs by hand, and everybody loved them, and it became iconic penny lane. And now we have a designer who makes all of those designs. So good question. And can you find global minima? It depends. It's actually the goal. That's what everybody wants. When you have your quantum machine learning problem, the goal that you want is to find that global minimum, right? The overall minimum. That is what you want. But depending on how you set your problem, what optimizer you use, and how your data is, how your cost function looks, sometimes it's going to be easier and sometimes it's going to be harder. So it will happen a lot. And as you're trying it and exploring it, you will for sure fall into local minima. And you'll have to be creative and find new ways and explore ways of either you have to change your cost function. Maybe you have to use something called local cost functions. So you know that their answer is around a certain area or something. So you're kind of restricting your problem to a specific part of your cost function. This can allow you to not fall into local minima somewhere else. There are many techniques. There are stochastic techniques. So this is like a whole big thing that you can explore. And sometimes it's very hard. So there's no way to know, is what I'm doing going to fall into a local minima? Usually, I mean, okay, I haven't read all of the papers. Maybe there's a way. But as far as I know, usually, you try it and then you have to just check that you actually fell in the right place.
Wonderful. And everyone is ready and eager to continue. So let's move the other questions to the end of the talk and go to embeddings.
Good. So I didn't make this picture. I got it from a colleague, but I just found it so fun. It does show a little bit how this happens. You have your quantum computer and your classical data, you just want to put it in, and it's not always easy. Yeah, as I mentioned, it is a bottleneck, and you'll have to find creative ways of getting your classical data in. So usually brute force doesn't always work. You'll have to try different things of how to put your data into your quantum computer without it being a roadblock. So this is one of the reasons why a lot of people are saying maybe we have to think about quantum machine learning in a different way, because embedding that data is hard. So maybe instead of thinking of quantum machine learning in like big data, right? I think some of you mentioned speed ups and a lot of data, etc. That's going to be hard. Most of the times it's going to be small and you're going to need to reduce your data a lot. So maybe we need to be smarter about how we're doing embeddings. They're called either embeddings or encodings. You're going to hear both terminologies, both are fine. And they're going to try to represent your data in the quantum computer. Something very important that you want to know is you want your data to be identifiable or being able to be different for the quantum computer. So for example, if you have the numbers 1 to 10, that is your data, and you wanted to put into the quantum computer, and you say, all of the data, I'm going to put it as a 1, then your computer doesn't know that they are different data. If you say all of this data is going to be fall between 0.1 and 0.2, it's going to be hard for the quantum computer to actually, understand the difference between all of these different data points. So usually you're going to be wanting to use as much of the feature space available depending on the embedding that you want. For example, and here we're going to start to talk about some embeddings. Some common embeddings that you're going to see are amplitude, angle, and basis embedding. There are many others. These are just some examples. So amplitude embedding is going to be, well, actually, maybe let me ask you first a question. No, I'm going to tell you, we don't have as much time for questions. So amplitude embedding is going to input your features, let's say, all together into the qubits. So if you have 5 qubits and you have a number of features, you can have up to 2 to the n features, which are your data points. And you can encode them as an amplitude vector, right? So you remember when you learned about quantum computing, you have, you have your probability amplitudes, and you can encode them in different ways. So you can have a lot of features encoded into less qubits. You want to try to make sure that, your data is not all like clumped together, so that you can actually get different amplitudes there. So you're going to have your data, for example, being normalized. In terms of angle embedding, if your data are angles, you want your angles to be between 0 and pi, or 0 and 2 pi, or minus pi and pi, but within that range, right? Because if all of your data is, let's say, between, again, 0 and 0.1, then all of the angle embeddings are going to be basically the same. So the angle embeddings are doing a rotation. You start with a value. That value, let's say your data is 0.1. And your angle embedding is going to do, in this case, in the picture, we have an X rotation. So we're going to do a tiny rotation. And that is going to basically prepare that initial state. That is then, you're going to put your ansatz after. So first, you have, your data. You have to start with your data. Then you do a way to put that data into the quantum computer. So in this case of angle embedding, it's going to prepare it as a rotation. You can use X, Y, Z rotation. And you can and you should pre-process your data to make sure that they're not all kind of the same rotation. So you want to actually use all of that feature space that you have in the quantum computer. And finally, and for this one, it's important. You can, I'm gonna put the simplest way of thinking about it is you can only use n features, which has to be smaller than the number of qubits. Meaning, if you have 5 qubits, or in this case, we have 3 qubits, you cannot have one layer with more rotations than the number of qubits, right? So if you had five data points saying numbers from 1 to 5, what you would need to do is you need to do several sequential embeddings. So you would have to first embed data points 1, 2, 3, and then you will have to embed data points, let's say 4 and 5. But this would be a different embedding, right? It would not be just all rotations in a single line. You would have to have like several lines, and this changes. This is There's like a hack that you could do, but usually what you would do with angle embedding is if you have, let's say, 3 data points, you encode them each in 1 qubit. And for basis embedding, this one like is different. You really just need like the same number of binary features as the number of qubits, meaning that if your numbers are binary, say you want to encode 101 in this case, then you can use this embedding to say, I'm going to apply poly X rotation to make this a 1. Then I'm not going to do anything and apply a 0, and I'm going to apply another poly X, and this is going to become a 1 as well. So again, you're limited in the amount of data that you can put into the quantum computer with this embedding, but it is very practical if you have binary data. For example, sometimes, you can have, the number, say, number 3, and then you can turn it into binary. You can turn it into binary and then encode it with basis embedding. So this is something that you can do with quantum computer. All right, so just as a wrap up of what embeddings are the way in which you put your data into your quantum computer. Most of the times we're going to work with classical data, but if you have quantum data, you will also need a way to embed that data into the quantum computer. There are different ways. Some work with the amplitude, creating an amplitude vector. Some of them work with creating specific angle rotations. Some work with like binary poly X or not. And there are many others. So there's like a time evolution one. The others are a bit more complicated. I would usually recommend angle embedding for starting. It's usually the one that's easier to understand. But if you want to try them all, then for sure go ahead. Now, layers. Layers are different, and here it's important to pay a lot of attention. Layers are sometimes going to be different in classical and in quantum. So in this case, you're going to have some blocks, let's say A and B. And on the right-hand side, if maybe you've heard in previous sessions, block number B, you could say these are kind of like 2 or 3 layers, right? But for the context, let's say it depends on the context that you're hearing it, right? Because very often, for example, in Penny Lane, we refer to layers in the same way as classical layers, where you have a combination of things that go into a block A and a combination of things that go into a block B. And so A is one layer and B is another layer, and you can interchange them. So it's very important when you're, reading, learning, doing code, etc., to understand what terminology of layers is being used, whether it's the one where you say there's a block with stuff in it, or whether you're meaning like a specific, let's say a specific time step in, your quantum program. So here, for example, how many layers do we have? It depends on who you ask. I don't know if you've learned before the other different interpretations of how you consider layers, but for practical purposes, I think it's smarter to go with a classical machine learning concept of layers, which is just A is a block of stuff in a specific, setup, and B is a block of stuff in another setup, and each of them is a layer, and then I can apply them as needed, and I can apply more than one, etc. So here we have an example of parameterized layers. First, we have an embedding. Here we have angle embedding. We have Y rotations, and they're embedding our data, which are angles, pi over 4, pi over 3, pi over 7. We're embedding this data, and then we're adding a series of layers. We have some parameterized layers taking some angles, theta 0 and theta 1. They are being added as Z rotations. Then we have some C-naughts. So here you can consider this like an entangling layer. And then you can have another parameters layer, making rotations y and x on other values of theta. So here we can probably input into the program just a whole thing called theta, which contains all of the little values of the rotations. And at the end, we will have a measurement. So what this represents here is an expectation value. It's a very common way of obtaining measurements. Ansätze. This is one one that is very confusing at the beginning. But what it means is it's like an educated guess on the layout of your circuit. So you're not gonna worry about the specific parameters. So here, for example, we have some specific parameters. When you talk about your Ansätze, or ansatz, it's all about just the layout of the circuit, saying I'm gonna apply some Z rotations here, some C naughts, some Y and X rotations. It's all about the layout and not specifically about the parameters that go inside. And there are different Ansätze depending on what you want to do. So for example, circuit number 1 has some layers alpha and beta, A and B, which depend on alpha and beta. But circuit number 2 has also depends on time. So it has some exponentials, some evolutions, and they also depend on time. So it's going to be very important to, choose the right ansatz for your problem. And time-dependent things are hard. You actually have to do a lot of approximations, and there's a lot of research on how to do better approximations for those Hamiltonians. I hope you have heard of Hamiltonians. But anyway, you have like these matrices that you want to, exponentiate or evolve with time, and how to put them into the quantum circuit in a way that is efficient. That is a research problem. So yeah, Ansätze, it's not a solved problem. There's no one that works better for all, and you'll have to test them depending on your situation. So my recommendation here would be look for a similar problem to the one that you're tackling and see how they have performed the layout, that Ansatz, how they have designed it, and what approximations they have done. Because very often you'll have something that you want to, represent a specific physical problem, but you're going to represent it exactly. So that is something that I would recommend you take into account when you're looking at your Ansatz. Here are some formulas. So I don't know if you can tell, but they are different. The one on the left is a tree tensor network. So it has kind of like this tree structure where you have, kind of like a pyramid. You're going to think of it kind of like a pyramid. And on circuit number 2, we have something called matrix product states. And so here you don't have like that tree structure or that pyramid structure. You have kind of like layers that overlap at certain points. So these are also 2 different options for Ansätze, and these are useful for if you're working with tensor networks, for example. These are some that are gonna come, and it's good to be familiar with the concepts. So tree tensor network, matrix product state, they are ways of creating that layout of your circuit, and they're going to encode, you're going to encode your parameters in them, and it's going to have a different effect. So let's say you made a circuit for your project that you're going to go do at the end. It doesn't work. Try to change the ansatz. Maybe it's not good enough to represent, the solution that you want in your circuit. Try to see other options as well. Now, I guess we know about measurements, but they are important. It's important to remember that when you measure, everything becomes classical. So just be aware of it. Be careful of whether you're using an expectation value, samples, probabilities. You have all of these options, and they're also part of the circuit. So this kind of completes this different part of the circuits. Your encoding or embedding is where you will put your data into your circuit. And in some software, you might have the impression that you just initialize and it starts in a specific state, but in reality, it doesn't start in that. You have to put it in a specific state. It always starts in 0, and then you put it in a specific state with your encoding or embedding. Then you have your ansatz, which is your layout of your circuit, where you're going to have your parameters and you're going to be able to vary them. And at the end, you're going to have your different kinds of measurements. So I am going to show you a little bit of code quickly. And we're not going to do the live coding because we are not going to have enough time. But, oh, I think there are some questions that I hadn't seen. I'll answer them later. I'll answer them later because I think we're going to run out of time.
Yes, those questions are being asked on Discord, and Vardaan will ask them to you at the end.
Perfect. Okay. All right. So what I want to show you first is if you want to use Pennylean, for example, you can use it in Google Colab. I think, yeah. Anyway, I'm going to run this just in case I want to run something. So you import Pennylean as QML. So Pennylean is not only used for quantum machine learning, but it did start like that. So for historical reasons, we keep the kind of the signature here. You then create a device. So the device is going to be like the backend where you're going to run your circuit. Here, we're going to use a simulator. This one is called default.qubit. And you're going to see a lot that we say wires. Why wires? Well, if you look at a circuit, the qubits kind of look like wires. You know, those horizontal lines, they kind of look like wires. So we're going to call them wires, but they are qubits. You can say it's the same as qubits. Now you can create circuits in a very Python native way. So you create a function. In this case, I'm going to call it circuit. And you add the different gates in the middle of that function. And at the end, you return a measurement. Here we have at qml.qnode of dev. So basically this line, again, signature Pennylean, it turns your quantum circuit into something that you can run on a specific device. So your keynodes are going to be very important. You can then draw your circuits. You can even choose different styles. Here's the Pennylean style for those who asked about the Pennylean style. This one is automatic. So this is not a designer drawing it after every circuit. This is automatic. And you can also say, run your circuit and show you have 50-50 chance of getting 0-0 or 1-1. So you can then practice changing all of these things. So this was just important information to be able to read a little bit what's going to happen now. So this example, what we're going to show is I'm going to show you how to create a circuit that will learn a sine function, right? So this is a quantum machine learning problem. You have, we're going to have 10 data points from 0 to 2 pi. And we're going to teach the circuit. We're going to make it learn that it has to output the sine function. So we first, step 0, get your data, prepare the data. This is very important. In this case, it's just 10 data points between 0 and 2 pi. And I'm also creating 10 test data points that are a little bit shifted. I create a device. So the device is where I'm going to run my circuits. And now here we go to the interesting thing. So I know everything else was very quick, but I just want to focus on this specific point. Our quantum circuit takes some parameters. It takes some arguments, my data point and my parameters. So notice how I had actually 10 data points, but I'm going to run my circuit only once for each because I want to just here get at the output, at the measurement. I just want to get the sign of the specific input, right? I am going to encode the input as an X rotation. So with this gate, which is the first gate here, I'm going to modify the state of my quantum circuit. And then my circuit is going to learn the parameters of the next two gates, the Y and X rotations here at the end. It's going to learn the right parameters so that the output is always the sine function of whatever state, whatever input I had. So this is pretty cool. I just need one gate to do my encoding or embedding. So notice how this is an angle embedding. And then I have an ansatz, which is composed of a Y rotation and an X rotation. So I don't have to care exactly about the parameters that go in, just about the layout. That's going to be my ansatz. And at the end, I'm going to measure an expectation value. So a number that is going to tell me, give me the answer or a prediction for that sine function. That's what I want. Notice that so far I haven't said anything about the sine function. The circuit doesn't know. So what is the part that knows? I have a loss function and a cost function, and they're the ones that are going to help me, make the circuit make the right prediction. So what is the difference between a cost function and a loss function? They, in some cases, they can, be used for the same, but there's like a technical difference, and it's that you have 10 data points. Because we have 10 data points, then we actually need a loss function to calculate the specific loss for each one, meaning it's going to compare each data point with the expected output and the real output. So for my number one data point, which was 0, I'm going to, compare the prediction of the circuit. So for a specific set of parameters, I'm going to compare the prediction of the circuit with what we call the label. So you're going to learn that in the next section as well. You're going to compare and see, okay, if I did well, then this is probably 0. So we're going to have a low loss, and we're going to add them up, add that loss up. And at the end, our cost function will depend just on our parameters and our data and our labels. While our loss function here depends on our predictions and our targets. So our loss function kind of makes that comparison, and our cost function is kind of the overall function that we're going to try to optimize. And we can have more classical processing if we want as well. We can use different optimizers. In this case, I use a gradient descent optimizer, which is just a very normal optimizer. And I use an optimization routine. I'm not going to go into the details because I'm not going to remember. Maybe just remember my optimizer has some optimizing functions that are going to be able to help, like step and cost. And at the end, when I graph my results, what I'm going to see is that the parameters evolved. You can see that the cost is getting lower and lower, and the parameters are changing after every iteration, until it can always predict, even for data it has never seen, it can predict what are the right, it can predict the right output for the right input. So I know we're kind of out of time. So I'm gonna kind of skip a little bit of like talking about Penny Lane. Let me just give the homework. The homework is to practice. My homework is to practice, explore PennyLane.ai. You have a lot of practice opportunities and learning, tutorials, coding challenges, and a codebook. I absolutely recommend the codebook. The demonstrations are a little bit harder, but they also go deeper into what's going on in research in this topic. And the challenges are great practice. So the codebook is good to get started. It's not specific to quantum machine learning though. And in terms of the community, you can always ask questions. And I'm going to say the second homework, aside from practice, is ask questions, get involved, learn like you're doing with Womanium, like in the Discord, etc. Definitely, join the different communities because they're going to help you out. You don't have to do this on your own. So if you're still in that Menti, let me know how you like today's session. I hope you learned a lot. Yep. Let me know how you liked today, and if you liked it, yeah, definitely stay tuned for next time. And next time, I'll also show you the gate emojis. Gate emojis are kind of something you can add to Slack as well. So if you're interested, next time I'll show this to you. Thank you.
Wonderful. Yeah, thanks a lot, Catalina. We have already started receiving a lot of comments on our Discord channel. It was wonderful. Yaro says from Brazil. It was quite interesting. Very nice idea about predicting sign functions. It was very good. And we have a lot more comments too, but I can maybe just quickly squeeze in a couple of questions before we run out of time. One thing is about the collab file, which you just demonstrated. Can the participants get a link for that collab file?
It's not in a like public repo, but I can share, so Vardaan, I can share with you a blog post that has the sign function example. So that blog post has, it's a good way to remember what we talked about and also get the example at the end.
Perfect. So as and when we receive that blog post from Xanadu, we'll share it with all of our participants on this call. Another question, it's regarding ansatz and encoding. So while you were mentioning encoding, there were 3 different ways, right? One of the participants asked, is it possible to use all 3 of them or maybe a combination of these encodings in the same quantum circuit?
Good question. Yes, and there are more than 3. There are many more. These are just 3 that are kind of representative of what you usually do. So the goal of the encoding is that your initial state of your circuit is something that you can then, distinguish the different, each state kind of represents a specific data. So you can combine them, but you have to be careful so that you're kind of not diluting the data. So what you do not want is for your data to kind of like get faded out and then not distinguishable, because then your quantum circuit is not going to be able to act on each specific data point. But you can test it. You can test it and see maybe for your specific problem it will work.
Great. And then there's one question on the ansatz. So ansatz is an educated guess, right? So is it just a trial and error kind of way to come up with the best ansatz possible? Or is there a more structured way where the participants can actually work their way through and come up with the best ansatz for a particular problem or a particular quantum circuit?
Yeah, good question. So there's people who have done research for specific problems. So for the example that we showed today, we just use 1 qubit and 2 rotations. This is not enough to represent problems that I want to say are hard. And what does hard mean? It's actually complicated to say, but for example, a sign function. So circuits can be represented like in Fourier series, so kind of a combination of sign functions. If you just have one sign function, then that's easy. You just need kind of 1 coefficient. So that one is easy. But if you want to represent a straight line with like the same kind of layout, it's going to be very hard. You're going to need a lot of gates to do that. So you'll have to become creative and see how others have used different techniques to represent your specific problem. Because even a straight line, and I'll show this to you next time, a straight line can be hard with a similar ansatz like we were using today, precisely because it's not suited for that. And because it's so domain specific, it's hard to say. So for example, part of the research that Maria's team is doing is what is the structure of the problems and how can we use quantum computers to represent that structure, right? So it's not a solved problem, and it's depending on the problem, you have to choose one. You can use some generic ones, like a lot of entanglement, it can help, but you'll have to be careful because it doesn't work for all problems.
Right. Another question, and I'll maybe this is the last question for the day. Vardaan from India asked that, what is the physics behind quantum gradient descent in QML? Like, is it similar to how annealing takes place where the Hamiltonian is just left to reach out to the lowest possible state? Is something similar to that?
So annealing is different. Annealing is definitely different. And it's not about the optimization. it's about kind of like the whole thing, the whole picture. So if you look at the whole picture, you have these circuits that can do, they're universal. You can represent any, it's an information question. So in theory of information, you can kind of distinguish the two. In an e-link, it's like having a hot coffee and it kind of gets colder. Here, it's more like you are acting together in that coffee. You're kind of moving it around until you get something specific. So they're similar in the sense that they use quantum, but they're a different approach as a whole. It's not just restricted to the optimizer.
Great. Okay, yeah, with that, we can probably wrap up today's session. Thanks a lot, Catalina, once again, and we'll see you soon with the next lecture on QML and with Xanadu once again. So thanks a lot, Catalina, for today.
Thank you. I'm glad you liked it.